Okay, so as I mentioned, first thing I'm going to talk about today is getting that value from running in ArcGIS Pro, getting the total accumulated cost from the least cost path. Okay. So I know that my data that I'm about to bring up here isn't the same data you ran it on, but it'll still give you the total accumulated cost the same way. Oh, maybe I didn't save it. My computer might have crashed, but this will be pretty easy to do. So I don't even know if I downloaded the European data for the lab. I probably did. Was it the one that was just called data? Yep, it was. Okay. At least I'm pretty sure. So this was the European data for the lab. And I know that your steps were a little bit more complex. We're just going to calculate costs and then do least cost path, and then show you what I mean. Assuming this. Okay, yeah, it's added. Okay, there we go. All right, so here's Europe, and I need to come. Right now I have land cover. So one of the steps that you did was convert land cover into costs. So I'm going to do that. This was one of the steps. Under analysis, master functions. And remember how we converted land cover into land cover costs? What tool did we use? Remap, does that make sense? Remember that? Some people have been asking me, like, what do these numbers mean that I'm putting in here? Some people even said, well, I read the help on this, but I still didn't quite understand what was going on. So what we're doing here is we're taking the land cover raster, and we're saying that all values between the minimum and the maximum value will get this value. So when we say all values between 0 and 0, that's just the values of 0, are going to get 2. And then all values between 1 and 1 are going to get 5. I believe this was what we had originally. And all values between 2 and 2 will get 10. So that remap is what kind of operation? A local, a focal or neighborhood, or a zonal operation in ArcGIS, in GIS. What's that? Somebody say something? What's happening to the numbers? So we have a big raster. What's happening to the numbers? Like what's a good way to describe what's going on?
Remapping these new numbers
in place, yeah.
If you have this value, it then becomes that value that you're saying.
Right. And it's going pixel by pixel or cell by cell. So that's exactly what's happening. Is I'm only looking at one cell at a time, and I'm evaluating it based on this criteria and assigning it a new value. So it's a local operation. It's only happening in one raster cell at a time. I'm not considering the neighbors at all. Just the individual raster cell by cell. And if it's between 0 and 0, it becomes 2. If it's between 1 and 1, it becomes 5. If it's between 2 and 2, it becomes 10. I could put 2 and 4 here, and then what I'm saying is any value between 2 and 4 becomes 10. But I don't even have those values. I only have 0, 1s, and 2s. Okay. So I'm going to create a new layer from that, I'm gonna rename it. I'm just gonna call it land cover cost. Right? And then I'm going to run my least cost path on this data set. Okay. So I know that your actual land cover cost had to consist of 3 costs, but we're just going to do 1. Okay, so the next thing we're going to do is run the least cost path. All right, so here I select you should be selecting the total cost, not the land cover cost. And then, oh, that's the destination. So the destination is, the destination raster. The destination field, just value. The cost distance is oh, I skipped a step. What step did I skip? Based on what I need to put in here, I have costs, but I don't have cost distance, and I don't have the backlink raster. So I need to create both of those. So cost backlink and cost distance. Cost allocation, cost distance. There it is. So there is the source raster, and here is the land cover costs. I run that. I need to do the same thing to create the backlink. And this does take a few seconds to run on my computer. Probably take a little bit longer on those computers. It's not quite as long as the next step, which is the least cost path model. So we may leave that be for a second. Sorry, I thought I had all this already run, but it looks like it died. All right, so there's my cost distance raster. And then I need to do the cost backlink. So that's going to be the source again. And then the cost raster is the land cover costs. Create a new layer. Something wrong with this layer, actually. Let me see if I can change the symbology there. Okay. That looks right. Oh yeah, that's the cost distance data set. But remember, we need to symbolize it. Let's do classify. See what that looks like. Yep. And that makes sense because where is the source raster? Oh, I don't know why it's not displaying when I zoom all the way out, but remember the source raster is, the source is somewhere there in Venice. So as we zoom out, it's increasing. All right. So finally, in order to get this show on the road, we need to do the cost path and say the destination raster and the cost distance one is this one, cost backlink, and we want to just do best single, create new layer. All right, so what it's going to do here is find that least cost path. And you don't need to worry that if yours doesn't look like mine, because see the least cost path is traveling right through there. Yours won't look like mine because mine just did land cover cost. So if yours does look like mine, you might actually be a little bit worried because I just did the land cover cost rather than all of them. Okay, so we have a layer that represents the cost associated with traveling through every single cell. Okay. Which layer is that? Oh, by the way, so I told you that it's in the attribute table. If you right click and you can look, there's not even an attribute table, it says, right? Okay. Oh yeah, the people in Stennis weren't on the line. So now what we're trying to do is figure out the total accumulated cost for traveling along that path from start to finish. Okay? And you'll notice that that path has a value of, based on the symbology, what value does that path have? Based on what you can see here. 3, right. It has a value of 3. It's all 3s everywhere, except for at the source, it's 1. Okay? But we want to ask the question, what is the total accumulated cost of traveling along that line? And it's not in the attribute table if you did it as a raster function chain, which is the way I changed the lab over. I said the lab, I had the lab do raster function chains this time, and I need to modify the lab because the lab says, hey, you can look in the attribute table to find out what the total accumulated cost is. Well, it doesn't do that in the raster function chain, so that's wrong. But I still want you to find out what the total accumulated cost is. And that's kind of the thinking question in the lab. How do I find out what the total accumulated cost is for traveling along this line? And so what I want you to ask yourself is, how do I find a statistic for anything based on one raster having all the same value for that, for a particular area or zone? Do you remember that?
If it all has the same value, you just take the sum of all the opposite touches of that.
It's exactly right. So we need to find out what tool does that, because that is exactly what we want to do. So here is the cost. Your cost will be different. You should have a total cost layer, but here's the cost I used, the land cover cost. I want to add up all of the values underneath of this Pepto-Bismol colored raster that are underneath to get the total accumulated cost. In other words, the total cost for traveling along that line. So if my cost was in days, let's say, then the total accumulated cost would be the number of days it would take to get there. I mean, I'm not saying it is in days, but if it was in days, then that would be the total accumulated cost of traveling, whatever cost that's in. So we need to take that land cover cost, and we need to do that. So what tool does that? What tool allows us to sum up all the values in another raster based on a zonal raster? Okay, because this doesn't look like it's a zone, but it really is a zone if you think about it. It's just a zone means that we've labeled a certain area and called it something. And here we've denoted that this is the best path. So if we want to find out what the total accumulated cost of that best path is, then it's a zonal operation. We're accumulating all the values underneath this line into the final answer. Okay. So
So this is Erin. I use the zonal statistics as table function, and I used my cost path as my input raster, and then for the zones I used the total cost map. Is that correct?
okay. it sounds like it's almost correct. So zonal statistics table is the tool that I was picturing that you would use. Um, so I didn't get all of it, but
So right there, I put my cost path.
okay. So the zone data, yes, would be the cost path. Yep. The zone field is just the value. So what about the value raster? What'd you say?
I put my total cost map
Yes, that's right.
for that specific path because I have 2 paths.
What's that?
So I did 2 of them for each path, for the water path and the land.
That's it, right. Exactly right. She said she did 2 of them. One for her her path that went out over through the ocean, and the other path that went through the land. And so that's exactly right. You do that twice. So now we're going to run this. You could change this just to sum if you wanted to. But you can leave it on all. All will give you the sum. So either way. And then you run it, and then once that's done, you can look and see what that value is. Okay, so here is the sum. So mine's going to be different number than yours because I just did land cover cost. But you're going to have that value right there, and that's the total cost for traversing that path. Okay. All right. Now, I actually got a ton of emails about that. So, and the lab is written poorly about that part because it says it's going to be in the attribute table, and it's not. It's not in the attribute table. If you followed the rest of the directions, it's not in the attribute table. But anyway, just ignore the part that says it's in the attribute table, and I still wanted you to do this part. I say, what if it wasn't in an attribute table? How would you get it? This is how you would get it. Now, if you wanted to check to see if that would match the real value, you could run it you could run the cost path You could run the least cost path tool here, input your cost surface, which is this. Oh, this is that what I want? Yeah. This is the starting and the ending. So this actually calculates everything in between for you. But yeah, there we go. That's the one. This is the one that builds off the other one. So we calculate a destination, and then I'm just going to use the destination raster, so it'll match up. And then the cost distance raster, and the backlink raster, and then we need to make that the best single to keep it consistent, and run that. So this is the equivalent tool, and but if you look at the attribute table here, you could see that it does have a path cost. That number isn't the same.
Yeah, that's what I noticed in mine. I have to do it, and if the numbers are the same for me, they're open.
The sum of all of those values. Now there's a third way to verify and see which one it is, because remember that the cost distance raster, this one right here, What are the values in the cost distance raster represent?
Everything that's not bound.
They represent the cost to travel back. So theoretically, not theoretically, the value at the end of our destination, this cell right here, if we get that value, or we get that cell right there, cost distance. So that's 9017286. So that's actually the right number. So why did we get this number here? The sum of the values.
I don't recall exactly what I did, but I know when I did mine, I got the big number like you got, but it was in the payment instead of down there.
Yeah, if you did it doing the least cost path, you can get it. All right. Maybe I did something wrong. I have to go back and look at the video. But you see how the number in here equals the number from just clicking on the cost distance right there. So that's the total cost distance to get there. All right, well, yeah, I'm not sure, but that's one way to get the value. So you could just click on your cost distance raster at the destination to get the value as well. So you can put that in the homework too. All right. During the break, I'll investigate this and see. I'll go back and watch the video and see if I messed up and how I got that value. But yeah. All right. So I'm going to save this. So now I'll have it. I'll close this down and open up ArcGIS Pro. And get courses. All right, so today we're going to talk a bit more about terrain data. And I know that probably in most of your introductory GIS classes, you talked a bit about terrain data, but we're going to focus specifically on some kind of pitfalls and do's and don'ts when you analyze terrain data, rather than just talking just about the data itself. We're going to talk about all that. All right, so yeah, we're going to talk about terrain modeling. And there are a number of different derivatives that you can calculate from terrain data. When we talk about terrain data, we mean data like you have here of the state of Mississippi, where every raster cell represents a elevation. And that elevation can be the height, it is the height above some datum. You think about elevation, what is elevation? What do we usually think of it as the height above? Sea level, right. And sea level, though, it's arbitrary just as much as like the Celsius scale uses the freezing point of water as 0, right? I mean, we just chose the freezing point of water. It happens to be a convenient thing that we think about. 0 Celsius means that water is going to freeze. but there's nothing that says we had to choose that value. In fact, some other guy created a temperature scale that is actually in wider use here in the United States, where 0 is just the coldest temperature that he experienced over the record that the time period that he set out to create his scale. So 0 was just the coldest temperature he encountered, and that's why it's below freezing, because somewhere in Europe is where he was creating it. And that's the Fahrenheit scale. So we could decide tomorrow that we wanted to make 0 the very lowest point in the ocean, the lowest point on the Earth. But we've decided to make it the sea level, which itself is problematic, right? I mean, if you've been to the ocean, it's moving around all the time. Now, it can have an average value, but pinning that down is also problematic. And so there's lots that goes into saying what 0 is. Okay. Now, sometimes there are other ways to measure it from mean sea level. So sometimes when you deal with elevation data, they might say that this elevation data that you're getting is based on something that they might say is an ellipsoid height or geoid height. And that it means that it's based on a mathematical model of the Earth. In other words, instead of just referencing it from an empirical measurement of mean sea level, we measure the Earth and decide that the Earth is some perfect sphere or perfect ellipsoid, meaning that it's a little bit fatter, wider than it is tall, and then we try to fit that ellipsoid to match the shape of the Earth, even though we know that the shape of the Earth itself undulates. So that is something to pay attention to when you deal with elevation data. Is just like the coordinate system in terms of the XY dimensions, there is different ways to reference that Z dimension. Where am I vertically? Okay, is that a height above datum? Is that a height above the mathematically described mean sea level that changes? So that datum changes over time with better and better reference marks. So you gotta think about which mean sea level measurement am I talking about. So what I'm trying to say is comparing two elevation surfaces isn't always apples to apples. Sometimes there needs to be some math that goes on to compare those two elevation data sets. Now, we're going to talk about, the first thing that we're going to talk about is all of the different operations that you can do with terrain data, and then we're going to review them because lots of times these were taught in an introductory level GIS course. But we're going to get we're going to talk a little bit more about what to consider, how these analyses are actually performed inside the computer system. So the computation that goes into each of these, and why that's important. Okay. In other words, when we think about what slope is, now that we've learned about focal operations, neighborhood operations, slope is a neighborhood operation, and so we need to consider what happens. Like when a neighborhood operation is done, we're looking at the neighboring cells. So it's going to cause some problems when we talk about precision and accuracy of the slope measurement. So anyway, these are kind of a review of all the different operations that are available in most GIS software packages. You can see a summary of what they are. We've got slope, which is how the elevation or the raster beneath it is changing. Aspect is which direction it's facing. We are going to talk about upslope area and flow length, but not not in today's lecture. And we'll also talk about these other profile, curvature, plane curvature, visibility. We will talk about those today. So we'll talk about these when we talk about modeling water flow off of the landscape. But we'll talk about these other ones, how they're actually performed today, or how the mathematics behind them. So I believe I covered this mostly, except for we didn't talk much about the sources. How do we get digital elevation models? And really, we can get digital elevation models of all different precision levels. So having digital elevation model data everywhere in the world is actually relatively new. The first time that we had a pretty good global digital elevation model was in the year 2000 about. Okay, the space shuttle launched a radar instrument. So it actually, the space shuttle went into orbit and it put out a boom, and that boom sent radar signals down to the surface of the Earth that could penetrate tree canopy a bit, and it created a global 30-meter digital elevation data set, except for the poles. And up to that point, we had some data, particularly in the United States. We had patched together a nationwide 30-meter and even 10-meter data set, okay, based on photogrammetry, the first one. Okay. So now you can get global. At first, they didn't release it as a global 30-meter data set. It took actually another 10, 12 years. So just this past decade that we just had to get a global 30-meter data set. At first, it was only released at 90-meter level throughout the world, and 30 meters in the United States. All right, so that's an example of a radar instrument, but there's also radar instruments that are attached to airplanes that fly across. And basically, to sum it up a lot, to simplify it a lot, radar works very similar to the way that it works through parallax, basically taking a measurement from two different locations at the same time and looking at the difference. That's really the way our eyes sense difference. I mean, sense elevation and differences in depth as well, right? Like, if you only had one eye, if you moved back and forth, you can tell how far things are away from each other because of the way they're changing. But because we have two eyes, our brains interpret we don't have to actually move around to see things moving and to understand that this object's in front of that object. Even that small difference, that small parallax in terms of what we can see allows us to make those differences. And so radar and photogrammetry both work through that basic principle, that taking two looks at a particular area and looking at the difference we can triangulate the position of that object. And mathematical principles allow us to come up with a fairly, depending on the instrument and how it's used, a fairly accurate measure of where that object is located in space. Right? Now we can all send up our own personal remote sensing vehicles. You can buy a drone at Best Buy and fly it around. And there's photogrammetry software you can feed in the images. And as long as there's enough overlap, you can actually build your own digital elevation model with data that you collect from just a consumer drone. It looks something like this. So here's the USM Stadium, and turn off the ortho mosaic. So the colors represent the elevation. So just through the principles of photogrammetry, I'm going to try to make the transparency, opacity, there we go. There we go. The colors represent the elevation. So I've created a digital elevation model of the USM Stadium. So you can see these areas are higher up, the tops of the stands, than down there. And I can actually take measurements using photogrammetry. So even before we had drones, though, we could send up an airplane and do the same thing, or a kite. I don't know how practical that would be, but the secret is if you have overlap, multiple pictures taken from different positions in the sky, the software will infer the elevation that's below it. Okay. All right, there's another technology called LiDAR. It stands for light detection and ranging. And light detection and ranging is basically, well, it depends on a few different technologies. One is laser range finding. I don't know if these aren't really consumer devices, but there are devices out there that you can point them at a wall or point them at whatever you want, and it'll shoot out and tell you how far away that particular object is from you. And that works by sending a laser beam out. It bounces off the wall or whatever object it encounters and coming back, and you know how far away it was. Well, if you combine that with a very, very accurate location device, then you could figure out your position and the position of the end of the laser beam. So a LiDAR instrument sends out thousands of pulses per minute as it's mounted on either a UAV, an unmanned aerial vehicle, or an airplane. It sends out thousands of pulses per minute. And those pulses are directed toward the ground, and it uses those returns to turn that into a digital elevation model. At first, it's just a bunch of points. So that's another source of elevation data. And then finally, you could just do it the old-fashioned way. You couldn't do it in this big of an area, but you could do it using a survey, a very precise measurement. You could get a very precise measurement if you just went out with a survey-grade GPS or a survey-grade GPS coupled with a measurement, a laser rangefinder and an angular measurement. Sometimes they call that a total station. And you could survey in a number of points and turn that into a digital elevation surface. Okay, we'll talk about the process of turning point data into a surface later. Okay, that is something that we cover in this class. But right now, I'm just going to say that you can use that. So all of these different sources depend on a variety of factors. The error depends on a variety of factors. It depends on the source, but also the precision of that particular instrument. So if it's the shuttle radar topography mission, you're going to get 30-meter data that's not quite as accurate as a drone that's flying 200 feet above the surface, but you're not going to cover as large an area. You're never going to map the whole world with your drone that you bought at Best Buy, or even a drone that you paid, $20,000 for. Still not going to map the entire world with that. And so you can have digital elevation models that have all the way down, theoretically, like 1 sub-centimeter level, all the way up to, now we have a global data set of 30 meters, but before we could say 90 meters. So it's important to know, like for your project, the elevation data that you're considering using, what is the source and what's the accuracy and the precision of that source. Also, sometimes digital elevation data gets labeled as either being a DEM or a DCM. particularly now that we have more precise instruments, a digital elevation model usually assumes that we're talking about the Earth, the elevation of the Earth, okay, without any objects on top of it. Sometimes, I forgot to put that on the slide, but sometimes they actually refer to one that explicitly does not include objects like buildings and trees. Sometimes they call that a DSM, or a digital surface model. Now, we didn't even need those terms. You know, if we go way back to 20, 30 years ago, we didn't need those DSM, DTM terms. Those were just coming into being because a digital elevation model at 30 meters, it doesn't always really matter if we're going to include the buildings or not, because we're talking about a big area. We knew that the shuttle isn't going to... In other words, the fact that a building was there, unless we're talking about a really, really tall building, was within the level of error in a 30-meter data set. Okay. All right. Now, DTM is the digital terrain model, and usually what we would call a digital terrain model is that it includes the things like the trees and that sort of thing. Okay, the pits, the passes, all that. All right. So here's some examples of some LiDAR data. This is approximately 2-meter resolution. So in other words, the grid cells that we've created in our raster data set are 2 by 2 meters. So we would call that nowadays, we'd call that, you know, moderately high resolution. A meter would be probably high resolution, and anything under a sub-meter would be great. Probably created from a UAS or something that was even closer to the surface than an aircraft. Okay. So when we take a bunch of points that we might get, all of these sources here, except for the radar, create a bunch of points on the landscape. That's what photogrammetry does. That's what LiDAR does. That's what surveys do. The radar creates a different product, and so usually what's delivered is actually a DEM surface. Okay. So when we want to create a surface from points, we have two main approaches. One of those approaches is to create a digital elevation model, and that is regularly spaced points. In other words, something like this. So every 2 meters, we determine what the value is, and sometimes there's a point pretty close by, and sometimes there's not. Okay? That process usually is called interpolation. Another method for creating a digital elevation surface or a terrain surface is using a triangulated irregular network, a TIN. Okay. So here's the difference between what we're talking about. So if we had a bunch of LiDAR points, these points right here, that represented, those are elevations, or they came from photogrammetry. So in other words, the way that works in photogrammetry is that the computer software recognizes the same object in more than one image. Sorry, more than 2 images, and at least 3 images. And so then it can infer what the height is. So all of these points have a height associated with them. And so we could turn that into a regularly spaced grid using interpolation. Or what we could do is build a bunch of plane faces. And I'm not talking about airplane faces. I'm talking about planes, like a mathematical plane. How many points are necessary to define a plane in math? It's 3. Yep. 3 points are necessary to define a plane. So that's why these are all triangles. So each of those 3 points has an X and a Y and a Z. And they're connected by 3 lines, and the space in between them is the face of a plane, so it's flat. It's modeled as being flat. And I don't mean flat like this. I mean flat as in it's constantly changing in two directions at most. That's what a plane is. Okay. So they could be offset, but they're all planes. Okay. The tins, like as I understand it, I'm not an expert, but this is one way 3D worlds are created in like video games or virtual reality. Okay. GIS, same thing. All right, so these are some advantages and disadvantages to using a DEM over a tin. Basically, DEMs are regularly spaced, so there's a few advantages that are associated with that. There are also some disadvantages. Since they're regularly spaced, it is possible for them to miss topographic features, okay, particularly if your topographic features are of a smaller resolution than your grid. So if your grid cells are 10 meters or 30 meters, and you're trying to look at cars, you're not going to be able to see the car, okay, because cars are smaller than that. That regular pattern does allow you to get a nice uniform look at the Earth, and it's actually less complex CPU-wise. So if you load a DEM, it usually loads pretty quick. Whereas if you load a tin, it can take a long time because really you're looking at a bunch of points and making a bunch of plane surfaces on the fly. Another advantage to tins is that you can force tins to have specific contour lines in them, so you can actually really model specific objects in your tin. Basically, you can have a varying degree of complexity inside the tin. In some areas, you can be really coarse, and in some areas, you can be really precise. Whereas in a DEM, since it's regularly spaced, it's either 2 meter, 3 meter, 4 meters. It's, the whole thing it has the same resolution associated with it. All right, so in the end, we really are talking, when we say we're modeling terrain, we're talking about a height. And it is one of the most utilized GIS layers. It's used in all sorts of different applications. I just listed 4, but there's lots. And then there are also many terrain derivatives, with the most important being slope and aspect. But one of the things that we need to think about when we calculate slope is how it's calculated and why that's important. So slope is defined mathematically as the change in elevation, a rise, with the change in horizontal position. Now, before I get too far into this, we can calculate the slope of other raster data sets. So slope, in terms of, like let's say we had a data set that represented temperature. Okay? We had temperatures all over the United States. And since slope is the degree to which it's changing, if we had a slope map of the United States temperature values, what would the high areas represent? What are some ways to characterize those? So instead of using elevation, we feed in a data set that represents temperatures. And slope is defined as the change in, we said elevation there, but this would, if we put it in temperature instead, it'd be the change in elevation with a change in horizontal position. So it'd be the change in temperature with a change in map units, in distance. So those would kind of like be fronts, right? The interface where the warmer it is on one side and the colder it is on the other, the higher the slope value is going to be. The more change that's occurring. So slope is really a map of change. That's important to understand. We're mapping in mathematics. It's often referred to as the derivative, the first derivative. Like when you do calculus, we're not going to do calculus today, but when you do calculus and you calculate the derivative at a point along a function, you're calculating the slope at that point of a function. So we're doing that, but we don't have to use calculus to do that because our function is the data set in question, elevation, temperature, whatever. And we're going to calculate slope at a certain point. In order to do that, we need to consider the surrounding elevation data sets, and if they're really changing, we should have a high value. And if they're staying the same, we'll have a low value. That's what slope means. So we can use the derivative slope in other applications besides elevation, but we're talking about it here because it's a very common one to use in elevation. But if we took the slope of a temperature map, realize that the high values would be areas where spatially there was a rapid change between high and low values, or between low and high values, right? Let's think of another. Even if it was sea surface temperature, which is again temperature, then it would be areas where there was more change occurring in terms of the temperature. So the interface between a warm current and a cool current would show up more if we did that. Or wind patterns, or anything like wind speed. If we had ocean currents, modeling the slope of ocean currents, velocity would show us where it's shifting from going really fast to really slow, things like that. So really, slope is a measurement of the degree of change that's occurring. The way that it's calculated mathematically is that it's just the rise over the run. And since we're talking about since we're talking about space, the run is always going to be geographic space, like a distance. And the rise is going to be the change in the variable, which is usually going to be elevation. Right? So if we're going to calculate the slope between any 2 points, we would just find so this was 1 point, that's another point. We find the run and the rise values. Okay. We can also calculate, instead of calculating as a percent, we can calculate it in degrees by just taking the inverse tangent and then the inverse tangent of that value, and that'll give us this angle. So ArcGIS and actually many softwares give you the same options. You can calculate percent slope or degree slope. You can even convert degrees to radians and back, which we will do if you were curious on terms of the radians. Okay, so slope in a GIS is measured as the steepest direction of elevation change. Slope often doesn't fall parallel to raster values. We're talking about raster in this class. I'll walk through some water, so I'm trying to let my socks dry out here. Oftentimes it doesn't, in fact, most of the time, it doesn't, the slope isn't always parallel to the raster rows or columns. So we want to calculate slope in a certain area. We need to use the nearby cells because the slope of one cell, 44, how much is it changing? How much is this cell changing? If we ask ourselves that question, naturally, we need to look at our neighbors to find out how much this cell is changing, right? Because if we only have the value for just that cell, 44, I have no idea how much it's changing. Let's look at the neighbors and see how much it's changing at that location. So one of the first questions to ask ourselves is, which cells do we use if we want to calculate slope, to find out how much it's changing? There's several different methods. There are two methods that are most commonly adopted in different GIS software packages. So the most common one here is actually the second one, the third order finite difference. That's what's implemented in ArcGIS. The second most common one is just using the 4 nearest cells. So that would be this cell, this cell, this cell, and this cell. Okay. So in order to look at these calculations, the first thing that we're going to do is just consider those 4 nearest cells. But let's think for a second about a kernel. Okay, remember we talked about kernels before. This is a slide from the previous lecture. But what we're talking about is coming up with a kernel that will tell us the difference in this direction and the difference in that direction. All right. So here, remember we had the high pass filter where everything was -9 and the center was 9. So we multiplied all of the neighbors by -9 and the focus by 9, and then added all those values up. And that would basically accentuate noise. Well, what we want to do is accentuate change. And so the neighborhood kernels that we're going to use to accentuate change look just like this. Because if we go back to the math here, we need to figure out the rise and the run, right? Well, how do we figure out the rise, that first part? Well, we figure out the rise using a kernel that looks just like this. So the rise, this figures out the rise. If you look at, I'm going to make this big for a second because the numbers are hard to read. But if you look at the value here is 900 and the value here is 980. The difference there is 80. This kernel has produced a difference of 80 for that cell. Also, if you look in this direction, so I looked this direction first. If you look in this direction, the value is 940 and 900. And so that's a difference of 40. So in this raster, output raster, we get a value of 80. In this raster, we get an output value of 40. So which one's the slope? Because in one direction, the rise was 80. Sorry, in this direction, the rise was 80. And in this direction, the rise was 40. Okay, so which one's the rise that we want to use? Well, the way it's implemented in GIS software packages is that in the XY dimension, we take that value, and in the north-south direction, we also take that value. We take them both. Okay, so that's where those numbers come from. So in this case, 40 minus 49 would be 9, and 45 minus 48 would be 3. So we have those values here. So this would be 9, this would be 3. Now remember, slope is the rise over the run. So what's the run between these two cells if the cell size is 10, as it says? What's the run from here to here? Because we've got the rise. The rise is 49 minus 40. How far is the center of this cell from the center of that cell? If one cell is 10. 20, exactly. So that's what's happening in this formula. It's the rise, which will be 9, divided by 20. So 9 divided by 20 is 0.45. And 45 minus 48, since we framed it that way, so we did 45 minus 48 is -3, divided by 20 is 0.15. So we've got two numbers. So the way that we reconcile this is that we add them together after we square them, and then take the square root. And that will give us the slope as a percent. And then if we take the inverse tangent of that value, we'll get the slope in degrees. So we have our slope in percent and our slope in degrees. And so our slope in percent would be just this part. And then the slope in degrees is that number after we took the inverse tangent of that number. So 25.3 degrees. Okay. Now, most GIS software packages actually consider the diagonal values as well. So the diagonal values are also weighted in the equation. Okay. So researchers have studied this and found that this is a better representation of the slope. So how would you do that? Well, you might go out and actually survey in the center points of these values and figure out the true slope, and then plug it into this formula and see how close it got. Well, what we're doing is instead of just taking these two values, we're taking all three of these values and all three of those values and subtracting them. So we're saying 47 minus 42 plus 49 minus 40 twice, we're doing that twice, plus 52 minus 44, we're doing that once. And why would we divide it by 80 now instead of 20? Why did we divide it by 20 before? We were going from the center of this cell to the center of that cell, right? Well, now we've gone this one, and we've weighted this one twice. So we got 1, 2, 3, 4. 4 times 20 is 80. That's why that math works. Okay. So we get 0.39 and 0.16 here, and we get 22.9. So we do get different values based on the method. 25.3 versus 22.9. But this is the method that's most often implemented. What's the true slope? Who knows? Unless you go out there and actually measure it, that's the only way to know it. Okay. But researchers have studied this and found that the third order finite difference is more often accurate. However, what's the trade-off between these two data sets? Which one uses more neighbors? Well, this one uses more neighbors, which means more. It means more spatial autocorrelations occurring. In other words, your value is more dependent on its neighbors. So you are losing some precision when you do that, and that may or may not affect the accuracy. But yeah, go ahead.
So like in a case like that, say if where the 202 is, if the box is right below it's like off a cliff.
Yeah, okay.
Is that going to just mess up your data because there's a cliff there, so the elevation difference there is wrong?
Right, and then you'll get a different value.
Like on the football stadium, like if you're trying to get elevation on it, and then right beside of it, end of the stadium, you drop to the ground. Seems like that would mess up my slope pretty good if I was trying to do that.
Right. Yep. That might take a little while to download, but it's downloading, and yeah, we could run slope on there. Okay, but if we let's see. Oops, I meant to go to modules. Oops, modules. Okay. One time, I worked out a example. Let's see if I have that. If I had that. I mean, it actually wouldn't be that hard to put this in, right? So whoops, 42, 40. Yeah, it's going to take a little while, isn't it? 45, 44, 8. Sometimes people, they like math examples. So here is that same kernel in Excel. Make this a little bit bigger, and make these all kind of the same size. Okay. So this represents a little teeny digital elevation data set, right? So if I want to calculate these values out, what I could do is this value, so I could say equals this value minus that value divided by, I'm going to make this cell size, and say 10. So that's going to equal this minus, what's the right way? No, they were doing it the other way, which is fine. This minus this divided by that. And you have to put this in parentheses. All right, and then this would be, it's 4752, so it's this minus that is equal to this minus that divided by the cell size. That's going to be a negative number, yep. And then we can just fill this way. And then we can make these the weights. I'm going to weight this one twice, weight that one once. And then we say equals this times that. This times that. All right, so these are these individual terms. Then we need to divide everything. Oh wait, they did the division at the end. So let's actually do that. They just did subtraction. So I'm going to change these all to just that. We could actually do the division early. The math would still work out, but I'm going to do it the same way. Okay. So we've got all those values, multiply them by 2, and then we need to get the sum of all of them. So equals the sum of all these values, and then the sum of all these values. This is where they divided it by the cell size, so I'm going to do that right now, actually. Okay. So now we have these two numbers. See those numbers? What did I do? Man, those numbers aren't the same. I'm having problems getting the right numbers today. So 42 minus 47 is 5. 32 minus 7 minus 42, 5. So 5 plus 18 plus 8 divided by 80. Oh, yeah, sorry. It's the cell size times times 8. 8, and we have to put parentheses around it. And now we have the same numbers. All right. So we had those 0.39 and 0.16. Okay. So the this part of the formula, which will just be the slope in percent, we'll just do that instead of calculating the arctan. So this will be the slope in percent is this times this plus, oops, plus this times this, and then we need the square root of the whole thing. Let's put this in parentheses. SQRT. Squared plus, yeah. Okay. It's the inverse tan, right? I don't know if where that is in Excel. So let's just stay with the slope in percent. So the slope in percent is 0.42, so 42% slope in that area. Okay. Now you were saying, what if it was to just drop off in one direction? It should really increase the slope. So if we changed all these values to 1s, the elevation would just be dropping off there. So we should see this value increase or go negative, really, because depending on which direction, we're going to get negative values. But anyway, it should be higher than 0.4. The absolute value should be higher than 0.42 if we change all of these values. Okay. So yeah, we've made it like a ridiculously high slope if we do that. So that is what that will do. And what happens if we make all the numbers the same or make them more similar? 42, 45, and 47. See how the slope got less? It went down. It's a shallower slope. Okay. So now you might be wondering why that slope got above 100%. Well, it's rise over run, so it is possible because it's just telling us for how many you're going one direction, how many you're going the other direction, and as soon as that number becomes the 100% slope is what in degrees? Another way to think about that. 100% slope means that the rise and the run are equal. So what is that in degrees?
45.
45, exactly. So, if we changed all of these, we could probably get an approximate 40-degree slope, 45-degree slope by, or 100% slope by changing, let's see, so the change is 20. So we changed all of these to 10, and we changed all of these to 20, maybe one of these to 10 and the other one to 20. Made this one in between 15. It's not exact because it's looking at both directions, because now it's still like this direction is still 20, a difference of 20. This is a difference of 20, but this is still a difference of 10. Those are difference of 10, difference of 10, difference of 10. This is a difference of 0 though. But if we change this to 20, then all of a sudden now this is a difference of 20. But it went up regardless because we're increasing the slope. Okay. All right. That's just a little Excel example of what we're doing, how the math works. All right. Now, one thing to think about here is what's the maximum slope can get in degrees?
90 or 81 or 80.
Yeah, like, So a 90-degree slope means that it's a drop-off in real life, right? Like, so here's a stair, right? There's a stair here. So picture a stair if you're not here, and the slope that goes down a stair, the face of a stair, is a 90-degree slope because it's straight down. However, if you think about this, now that you know how it's calculated in ArcGIS, is it possible for you to ever actually get a 90-degree slope, like get the value 90? It's not, because you're always going to consider the cell to the left and the cell to the right. And in order to get a 90-degree slope, your value, your run needs to be 0, and your rise needs to be whatever. It doesn't matter what it is. But as long as your run is 0 and your rise is greater than 0, you'll have a 90-degree slope. But you can never get there with a raster data set. And so, although the limit of the value that you can get is 90, in other words, let's say we did have it'd be interesting if I could get if I figured out what the tangent formula here is. You know, but let's just say you made this like, 1, and this like 10,000, and if you had some crazy drop off like that, you can get really, 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 really close. Here we've got 50 for our 50% slope. So in other words, the rise is 50 times more than the run, but we can't quite get all the way there to exactly to 90. So if you turn that into degrees, we get 89.9999999. If you did have a big drop off, but you can't ever get there. Now think about, the bigger the cell size, the less able you're going to even be able to get to 90. In other words, like let's say we have a DEM of an area that does have some pretty big elevation changes. If we have a 1 meter cell size, then we can have slopes that get really close to 90. But if we have a 10 meter cell size, all of a sudden there's no slopes anywhere near 90. Now the highest we can get is probably in the 80s. And if we have a 30 meter cell size or a 40 meter cell size, we can never get slopes that even go higher than 70 degrees, because the run keeps getting larger relative to, and the rises still don't change. The elevation values are still fixed to be a range between 0 and whatever. So the point is that the resolution of your digital elevation model actually has an influence on what the maximum slopes can be. Does that sound like the slope is the slope, right? Like if you go out there and you experience and you see a cliff, it should be a 90-degree slope. But you're never going to be able to see 90-degree slope, and as the resolution of that raster increases, the slope is going to go down, even though in reality it doesn't go down, because it's always a measurement from the center of the cell to the center of the cell. So it's averaging all those values out. It's chopping off the edges of all those slope values. So that's why you need to pay attention. Like, in other words, if you calculate a slope value from a DEM, the slope value is actually twice the resolution in terms of the precision of that slope. So if you've got a digital elevation model that is a 30-meter digital elevation model, and you calculate slope from it, the slope value is really should be considered as the slope at, did I say 30? So it should be the slope at 60 meters. because it's twice that, because you're looking out in both directions from the center of the cell size distance. And that's what you're calculating slope from. There's really no way around that if you're using GIS data, but it is what you're doing, and so it's lower resolution. The same thing with aspect. I won't go through the math on the aspect as much. You're not gonna have to recreate the aspect calculation anywhere, but realize that it's using some of the same formulas or pieces of the same formula. So we're still looking at the distance in Z and the distance in Y. But you should know what aspect is. Aspect is the orientation of the slope. So it looks at those differences, and it can either be third order finite difference, or it can be the 4 nearest cells. And the output of an aspect raster, I think we've done this in class already, but the output of the aspect raster is a number between 0 and 359, okay? Because 0 and 360 are the same. Okay. Areas with a truly flat slope, in other words, if the slope is 0, then they're coded -1 in ArcGIS in the output of a slope. So if you're looking for flat areas, you could calculate aspect and then do a conditional statement or a remap statement that said, if it's -1, make it a certain value. Okay. All right, another derivative that is often helpful with terrain data is a viewshed. And unlike slope and aspect, I don't really see how viewshed would apply. Like if I did the viewshed of a temperature raster, I don't think that it would do anything important. Viewshed, what it does is it requires you to enter a source, kind of like the cost distance raster, and it will output all those areas that could be seen by an observer at that source. So based on the elevation. So another way to look at it in 2D would be like this. If this was my source, and you can specify an offset. So if I said, here's where I want to stand and I'm 6 feet tall, then the output will code all those values that are visible as 1 and output all those areas that are not visible as zeros, or sometimes no data. And that's what this is trying to show here, is that you get all those values there. All right. So if we were to do that, I'm going to call this week 5. And then I'm going to add in my trusty Laguna Beach data set. I thought I put that right in here. Maybe it's in week. Is where I have it. Should write that down. So I'm going to take my elevation data set, and I'm going to start my my start area. I'm going to run a viewshed. So what you need to do is you need to feed it your elevation data set, and then you need to feed it your start area. Oh, it actually wants it as a point or polyline. I think I have that as a point. Nope. Okay. I don't. Polygon to point. Feature point. Okay. So I'm gonna take my start area and turn it into a point, and then run view shed. Oops. All right. So based on that green dot there, if I was standing at that green dot, then I would be able to see all of the orange area. What might be an application for this this kind of thing? Like why might I use that? It's basically line of sight, right? So what are some applications for line of sight? In other words, there is a line of sight from this point to all of those locations. So what are some things I might use that for?
Deciding where you want to put, like,
Cell phone towers.
inside of the mountain.
A what point?
Like a full-off point, a viewpoint.
Oh, a viewpoint on the side of the mountain. Great. And then one of the two, it's Dennis, Aaron or Shara said a cell tower, right? Is that what you said?
Yeah, that's what.
Yeah. So some sort of radio signal. Okay, those are both valid things. One time I was at a conference where somebody did a military application of this. So what they did was they calculated the view shed from a bunch of different locations, and then they overlaid those together. Like, in other words, they just did cell statistics, and they found out which areas in a valley were more often visible from a bunch of areas, and they used that as like a risk surface. When we're in these areas, we are visible from more other areas, and so like as a kind of like an ambush type planning. So if we're more visible in this location, it's more likely that we could become a target. Okay, and so then I could see, that's as far as they took it, but I could see where you could then use that as a cost surface and then plan a route through a certain area. So you could say, okay, which areas are most likely to be targets for ambush, and then which areas do I want to avoid because of that. So if I'm going to drive through it, I can do a cost surface for that. So that's another application. But both of the applications that you cited are used, and I actually have an example on the slides here. Here's the viewpoint. These are the areas that would be visible. You could do, in fact, in my scenario last week where I was trying to do one of the costs was, the only cost was the slope. I wanted it to be a nice gentle trail. Well, what if I wanted instead of a nice gentle trail, I wanted one that always viewed a certain area? I could design a model for that. So let's say that, has anybody ever been to Mount St. Helens? Ever been to Mount St. Helens? So it's kind of cool. I've been there, but it looks like this, right? And it's just out there. You know, when you drive up, you can see it, and it's there. But like if I wanted to design a trail that went, let's say, up to the upper rim, but I wanted the trail to maximize the ability to see into the what do you call this? The center, the bowl. Then what I could do is I could create a bunch of view sheds, and then I could reassign. I could make it so that anytime the view shed intersected the area of interest, I could store that as the raster value for a particular cell value. And then I could use that as in a cost distance model to maximize the time along the path that you could see that. Build that as a that would be a GIS model that you could build step by step. Okay. That'd be taking this one step further. Okay. And it's kind of related to the military application, but it's more of a civilian application. All right. Shaded relief or hill shading. This is done for two basic reasons, and it's not always as apparent in that it is done for two reasons. Basically, hill shading is artificially illuminating the cells. So in this case, think about what the cells represent. The output cell represents how illuminated that cell would be based on modeling the sun's position. So we're going to model the sun's position as how high it is in the sky and its compass heading relative to the map. Okay. So if I say the sun is 45 degrees up, that means that it's roughly from the flat part of the horizon all the way to the top would be 90. So it's roughly halfway from the horizon to being straight up. That's 45. And then 315 means that the sun is in the northern part of the sky. Does that ever happen? Where we live? Is the sun ever in the northern part of the sky where we live? No, it never is. It can get directly overhead, but it doesn't get well, it actually can't get directly overhead, but it gets really, really close, right? So if you're on the tropic lines, it'll get directly overhead. In other words, it'll rise up from directly in the east and set directly in the east and go right above your head. But in the northern hemisphere, it'll just get close, north of the tropic. It'll just get close, but it'll always stay in the southern sky. And in the wintertime, it rises in the southeast and sets in the southwest. So actually, the hillshade that they've come up with here is not something that would ever actually occur where we live. The example that they've provided, the sun will never be up in 315, almost due north of where we are. Okay. But it could be due south at 45 degrees. That happens. Okay. It'll probably be close to the winter. Now it could rise, I don't know what that is. So 0 and 360 are north. So 180 is south. So at 130, it might be at 45 pretty commonly during the year at some point, during the day. But the point is, we could actually figure that out. There might even be a site on the internet that tells us where the sun is in the sky at any given time for any given place on Earth, right? And we can model the sun's position and create a hill shade to show us which areas were illuminated and which areas aren't. Why would that be important? Like if we were going to put that in as part of an analysis, why would it matter where the sun is? Yeah. So areas that are always shady will have different plants that live in them, which will cause there to be different soils and different animals that inhabit those areas because there's different plants. So if we want to model anything that has to do with that, it might be good to create a analytic hillshade. Now, cartographic hillshade is often done to be visually pleasing, to allow the user to see something. So look at this. This is my Laguna Beach data set. And you all understand, because now you've looked at DEMs a little bit, that these areas are low and these areas are high. But I'm going to do this as a raster function. I don't know, viewshed was what we just did. By the way, I could have done, I'm curious on here, because I haven't done that in a little while. Observer features. Oh, so they still take, so that one takes features. Elevation. This one should produce the exact same thing. I'm just curious real quick. I haven't actually run viewshed in, there we go. Yeah, so that doesn't look too different. That doesn't look too different than that, but it is a little bit different. Oh, it's because there are, oh. Well, there are 2 observers. I don't know why the first one didn't get both observers. In any case, that wasn't what I was trying to show you. Okay, so hillshade. So here we're going to take the elevation raster and do a hillshade. And if we say go, right now, it used those default values of 315 and 45. Those are the default values in our GIS. And so the sun will never be up here in this. So the sun's like up in this position and it's shining down here. That's why these are brighter. So some people can interpret. Most people that are just your average map readers will actually be able to interpret the elevation a little bit better this way than this way. Okay. Now, one thing that some people like to do is do a combination data. It's called take the color scheme, and we choose a color scheme that might be appropriate for an elevation data set. Right, like that. And then we could set the transparency. Where is the transparency? It should be opacity. View. It's not something that I'm as familiar with in ArcGIS yet. Anyway, I'll find that out. But you can change the opacity of this data set, and then you can see the elevation values through it. So that's an option. Okay. Analysis, raster functions. All right. Now, if we wanted to do a real an analytical hillshade to actually tell us which areas of Laguna Beach are more often sunny than others, we'd have to put a real value in. So we might say like 145 and 45. And now the sun is going to be closer to due south. It'll be actually almost the exact opposite. So coming from over here, and we create a new layer. Oops, I forgot to tell it that I wanted to use the elevation data set. So we create that. Now you see that. Now, most people, when they look at this raster, will actually misinterpret it. And some researchers say that it's because, most of the time we set up pages to read left to right. Okay, that's the way we read. And when we put something down on our desk to look at it, oftentimes the light source is in front of us, like if we had a lamp, or above us. And so when we look at this, a lot of people, including myself, I would agree, misinterpret these as ridge lines. Like this is a ridge line. Because I'm still assuming that the light is falling this way. And so if the light was falling that way, this would be a ridgeline. But in reality, the light's coming from this direction. So this is a valley. This is a trough. That's why you can't, that's why it's darker. It's shaded. So it's being modeled as being in the shade because the light's pointing this way and it's a trough. Okay.
So the ridgeline is actually the brightest.
This is the bottom of this is a road at the bottom of a valley. Yeah.
Like below that area is the higher points.
This ridgeline right here so the ridgeline runs right through here and it separates this dark. So this is illuminated because it's going up in elevation and facing this direction. This is dark because now we've crested and we're going back down into this valley, and this is the bottom of another valley, and then we start going back up, and that's why this is bright again. Yeah. So same thing here. This is going down into this valley, and this is the face that's facing. So most people, one reason why this is the default is because most people interpret that correctly as being this is a trough, and then these are ridges through that. Okay, so that's why that's the default. But if we were actually trying to analyze something, we would do this this raster, and there's all sorts of things we can analyze with it. We could be trying to find the habitats of something. If we were running a fire model, fires would probably be less likely to start in dark areas, things like that. There's all sorts of applications for an analytical hillshade like this. So, so the values returned by the hillshade. So we click on these values, we get a value of 110. The values returned by the hillshade may be considered a relative measure of incident light. So here's some examples. If you're locating a farm or solar panels, you may want to find well-illuminated slopes for them. Okay. So always use real positions for analytical hillshades. And that's that. So here's a shaded relief of the whole western United States. and some people would find this just as interesting, maybe more interesting than a digital elevation model, because you'd be able to see the basin and range sections through here. You know, we got a bunch of ranges with a bunch of valleys in between. You could see the Great Central Valley easily. You could see the Snake River Valley, the floodplain there, and it turns in Columbia's up here, just out of the picture. All right, so again, I'm not going to go through the formula here for calculating shaded relief, but it is just a function of basically slope and aspect combined together. Okay, so it does suffer from the same problems in that it is illuminating the surface as if it's twice the resolution of the original surface, because it's using slope and aspect as the major inputs. Okay. So this is the formula that goes into hill shading. You don't have to calculate that for the test or anything. Okay. It involves several steps. Obviously, you can see that this is a big step, but we can break the steps down into individual steps. Okay, we're almost done here, and then we'll take the break. The last thing that I want to talk about is this is just kind of an interesting way to think about modeling the surface that was presented a long time ago. This is you saw the paper. I think it was 1999 was the date. But what this will do is it'll allow us to incorporate this concept, which will involve doing some calculations in ArcGIS that in order to accomplish what the authors we're trying to get across, and that is thinking about slope and aspect as one single entity, right? So if you read the paper, what they argue is that slope and aspect can be stored together if we think about them as being a surface normal vector. And what a surface normal vector is at the center of every cell, we can think about the slope, however the slope is modeled. We'll still calculate slope the same way. However slope is modeled, if we store the location of a vector that is exactly 1 unit from the center of the cell out to its endpoint, then we've captured both slope and aspect by doing that. So if we store the XYZ location of this vector that extends out, and what we mean by surface normal is that it's only 1 unit and it's exactly perpendicular to the slope. So if you think about the slope as a plane, like a plane, it's sticking out of the plane exactly perpendicular to it. So as it moves around, it's always exactly perpendicular to it. So another way to think about it, okay, if the slope was perfectly flat, the beginning of the surface normal vector would be at 0, 0, 0, and the end of the surface normal vector would be at 0, 0, 1, because it would still have the same xy value, but the z value would be 1. Okay. And so if we tilt it to the east, then what's going to happen is that the x value is going to increase. If we tilt it to the east, the 0, 0, 0 will still stay the same, the base. But as it gets tilted to the east, the end point of the surface normal vector will go further this direction, the east, which is positive in math, right? In Cartesian coordinates, 0, 1, 2, 3, 4. So it will go, as it goes this way more often, as it tilts more and more this way, the x value will increase, and the z value will actually decrease because it was at its zenith. It is 0, 0, 0, 0, 0, 1, it was at its zenith. So it'll slowly decrease, and at a theoretical 90, we're not actually going to be able to get 90 because remember we're using the neighbors, but at a theoretical 90, that surface normal vector would be pointing straight east. So the end point of the surface normal vector at that point would be 1, 0, 0. X would be 1, y would be 0, and z would be 0. Same thing if it was pointing north, it would be 0, 1, 0, because x would be 0, y would be 1, z would be 0. If it's pointing due west, it would be -1, 0, 0, and if it's pointing due south, it would be 0, -1, 0. Okay, and so any position of that surface normal vector can be measured as a number between three numbers between between -1 and 1. So that's what they were arguing in the paper. Why would we do that? Well, the reason for doing that is that we could calculate, it would be easier actually to calculate some things that might be more important than, like, let's say we wanted to calculate the average slope. What is the average slope? Well, we could define the average slope in 2 different ways. One is that we just take all the slope values, add them all up, and divide by the total number of cells, right? But let's think about what happens if our raster looked like this. And we added all the slope values up. All the slope values here are going to be 30, and all the slope values here will be -30. So what would be the average slope for this for this raster? 0, right? It doesn't matter how many cells we have. We have 100 cells here, On 100 cells here, these will all be 30, those will all be negative 30, the average will be 0. But does that accurately represent the average slope there? Well, in some cases it might. If we were considering what's the average, if we were to travel from here to here, what is the kind of like average that we would, if we averaged out the elevations, yes, it would be 0. But that's not what we often mean. If we were to travel from here to here, more often we're concerned with what was the average local slope that was occurring all the way along the way. And so in this silly scenario, you could just say, well, why don't we just take the absolute value? However, that wouldn't work if we have slopes that, like if this was actually like a cone, okay? We want to capture that value. What we could do is calculate these surface normal vectors first, then calculate the average position of that surface normal vector, and then we would get. So I said 45. I guess it's 30. I mean, I think this looks closer to 30. But we could calculate the average position of that surface normal vector, and we would get a value of 45 as the average slope in that case. So that's one application of it. There are several other applications that are argued about in the paper, so it does have a pretty straightforward implementation, and we're actually going to implement this in the lab. So this is one of the things that we're going to do, and this is just a flow diagram, and we're going to implement this flow diagram. We're going to create the surface normal vectors. We're going to do this for our data set. We're going to use some Mount Shasta. I can never say that right. I should probably switch to another area. It's another mountain in the Cascades, like Mount St. Helens. We're going to use. We're going to calculate some data using Mount Shasta, and we're going to calculate these x, y, z values from slope and aspect. So we're going to calculate slope and aspect, and then we're going to run these. These sine and cosine values. We're going to have to do a little bit of other things because by default we want them to be in degrees or radians, but we'll figure that out during the lab. Here it is in a model, in ArcGIS Model Builder. Okay, so I have that already all laid out for us. Yeah, so when we calculate slope, we're going to have to convert degrees to radians because the cosine tool accepts degrees and radians. Okay. But other than that, this flow diagram and this flow diagram are very, very, very similar. And we're probably going to implement this in as a function chain, but we could do it that way as well. All right, and then finally what we're going to do is come up with the mean slope and the mean aspect using this table and compare it to the mean slope and the mean aspect, just calculating the zonal means of those areas. So that's what we're going to do in the lab. All right, so let's go ahead and take a 15-minute break, come back at 3:20, and then we'll work on the lab, and I will come up with a number that you need to turn in for the lab in terms of the least cost. I'm going to go check that out one more time.